Hello and welcome back to CST 3130. So in this lecture I'm going to introduce relational databases. So you can start with a sort of introduction and the basic concepts behind them. Then I'm going to explain the piece of software that you interact with when you're using relational databases, which is called the Relational Database Management System. Then I'm going to go over some of the basic concepts like databases and tables, primary keys and foreign keys. And in the last section of the lecture I'm going to explain how you design a database using first normal form, second normal form and third normal form, and give an example of that that's kind of relevant to coursework 1. And finally I'm going to explain about how you can back up your databases. So very loosely speaking, there are two types of database. We have the sort of old school kind of relational databases, which I'm covering in this lecture. And then there's a sort of quite a wide variety of non-relational databases that are often called NoSQL databases. So I'm just going to say a little bit about the differences between them. So relational databases are fairly rigidly structured, right? You have these sort of tables that have very specific relationships between the tables. You have the idea that each transaction, each interaction with the database will leave the database in a consistent state. And that's sort of formalized with this idea of these ACID properties, which I'll come to in a second. And with relational databases, we interact with them using the structured query language. So it's quite a rich language for sort of inserting, querying the data in different kinds of ways. And some examples of these kind of relational database management systems are MySQL, Oracle, Postgres, and there's some Microsoft one I can't remember the name of. So these relational databases have these properties called ACID, which means they're all so they call it atomicity, consistency, isolation, and durability. You don't worry too much about the theory about this, but what it really means is that there's a great deal of care is expended such that when you interact with the database, it goes from one consistent state to another consistent state, and the way in which you set up the database determines what that means in terms of consistency. So here's a sort of classic relational database. We have these various tables, contact, customer, so on and so forth. And then these lines here specifies these relations between these different tables. And each of the entries or in the database, each of the fields in the database, they have a specific type as well. So they're doing their best to kind of, specify sort of very tight relationships between the different pieces of data in the database. And so we use this structured query language to store and retrieve data to and from relational databases. And I'm going to cover that in another lecture. I'm not going to go into details of that here. So these are the kind of things, select, update, delete, and each of these statements or commands has a sort of quite a complex syntax associated with it with lots of different options. So just to sort of understand the contrast, we also have, in the last 10 years or so, we had development of sort of NoSQL databases, yeah? So these don't conform to that list of atomicity, consistency, durability, etc. And they don't use SQL, that's hence the name NoSQL databases. Normally you'd use kind of like a programming interface, like an API to interact with a NoSQL database. And a number of these different types of these have been developed, kind of key value, like kind of DynamoDB, which covered in coursework 2, document database, such as MongoDB, which kind of covered in second year, right? And there's kind of more esoteric ones like kind of graph, and I think it's kind of specialized ones that are used for kind of natural language processing. So MongoDB, many of you covered last year, right? We have this kind of JSON format of the documents, and then we have kind of a database, and then collections, and each of these collections contains documents which have like an ID, and then basically you can put anything you like within this JSON document, and there doesn't have to be consistency between the documents within a collection, which is very different from what happens with relational databases. So there's no sort of single database that's going to, save the world kind of thing. And historically, the NoSQL databases emerged because it's actually quite hard to distribute an SQL or relational database across multiple machines. If I want to have a single database that serves up millions of users, I can't just run it on one machine, I have to run it on hundreds of machines. But then dividing up the records can be quite hard. It's a problem of sharding, it's called, because obviously we've got these complicated relationships between the tables. Yeah, so that's one reason why people ended up developing these NoSQL databases that could be very fast and very scalable. Now they've kind of improved the scalability of SQL databases or relational databases. So really, if you're trying to choose a database, think about the consistency requirements, ease of integration, so on and so forth. Yeah. If I was building a banking system or a government system, almost certainly I'd go for an SQL database, because then you know that this database, the data in the database is going to be in a consistent state. You don't have to work as a programmer so much to make sure that each transition from one state to another in the database leaves the database consistent. Whereas if you're using MongoDB, it's so fast and loose, and if you can sort of change the structure of the documents kind of almost on the fly, and so there's no guarantees that it's going to be consistent. But on the other hand, that flexibility can be really great for an e-commerce website, for example, where products are changing all the time. We might need to add new fields to describe new products that are emerging, and so we don't want to have to redesign the entire database each time. So in that case, maybe a NoSQL database would be a better choice. So choose the right database for your application. Don't assume that, relational databases are always better or NoSQL database is always better. It just really varies what you're trying to do. Okay, so let's go into how these things actually work and take a look at a database management system. This is something that students very often get confused about, so I'll do my very best to be as clear as I can about it. Yeah. So database management system is the program that manages the data. Yeah, it's not a graphical program, almost never. It's a program that runs in the background. It can run locally on your machine. So I've got a MySQL running locally on this machine, but it could also run in the cloud, right? We could, access it remotely. And in sort of earlier sort of architectures for kind of web systems, they'd have like one server that was running database, and then database management system, and then like another system doing like the web server, for example, then talk to that database management system. So typically listen on a port or a URL, or an IP address plus port, that kind of thing. And then the database management system sits there managing the database. And other programs that want to interact with the database send commands over the network to store and retrieve data to and from the database management system. Okay. Try and get as clear as you can about this, because like I said, people sort of often ask me, oh, Heidi, that's the database, right? But it's not the database, okay? So this is kind of how it all works. Yeah, we have the database management system in sort of reddish color here, yeah? At the center, that's like a program, like, the MySQL or the MySQL daemon or the Mongo daemon, called daemons because they run in the background, yeah? And this is talking to the file system, yeah? So you never talk directly to the file system with database. You always talk to the database management system, and that manages the file system, and you don't have to know anything about that file system. Yeah, it'll be some complicated thing that's optimized for the various operations database needs to do, yeah? And then we have a number of other programs, like command line programs here, for example, or the graphical interface, so, Robo3T or whatever it's called for Mongo, or in fact it's called Mongo's Compass now, isn't it? Or Heidi, which I'm going to use in these lectures. So that's a graphical interface that talks over the network to the database management system. And we have command line tools like MySQL dump that talk over the network to the database management system. In your projects, you're going to build a web service written in JavaScript, and again, that JavaScript program is going to talk over the network, running on Node, talk to the network, and that's going to talk to the database management system. And your Java program is also going to talk to the database management system, but in that case, it's not going to talk directly to it, it's going to talk to it through Hibernate, which will then do all the communications with the database management system, again, over the network, yeah? So you'll find when you play around with this stuff, that it's very easy to kind of test and develop it on a local database management system, and then swap out the parameters, then you talk directly to the cloud, yeah? So I'm just developing the coursework for my second year module, and in that case, we're just going to use a sort of a cloud-based version of MongoDB instead of a local one, but it's very easy to change between the two, yeah? So hopefully that's clear what I mean by a database management system. Yeah, it's a separate program running in the background that manages the file system, and other programs talk to that database management system over the network. Now, relational database management system is just one that database management system that runs a relational database. Yeah, so like Postgres, MySQL, MariaDB, Oracle, all of these are the same kind of things. It's a program, runs in the background, manages the file system, and then what happens with a relational database management system is that these programs send SQL commands over the network to the RDBMS, and then that returns the data or does things to the data in response to those SQL commands. Yeah. Most relational database management systems support a core set of SQL functions or commands, but then they might sort of fine-tune or customize them kind of with extra stuff, as and required. But if you learn the core SQL, that should work on pretty much any relational database management system. So again, with a relational database management system, exactly the same idea. MySQL here would be running away here in the background, and then all these other programs talk to that program over the network in order sending SQL commands and receiving data. Yeah. So for this course, I've chosen to use MySQL, the relational database management system. It's very popular. It was part of the LAMP stack, which basically powered the internet. In between 2000 2010 roughly. It's free. You're welcome to use a different relational database management system if you want, but it has to be based on SQL. Yeah, you're not going to get any marks in MongoDB or DynamoDB in coursework 1. Yeah. So MySQL is free, it's high performance, widely used. You're not going to go wrong with MySQL, and pretty easy to use, based on SQL, many supporting tools, right? So, I think it's a pretty good choice. But obviously, MySQL is just one example, right? What you're going to be doing with your code is pretty much the same, regardless of which relational database management system, because the SQL is the same pretty much, as far as you're concerned, at least, yeah? Now, there was some kind of controversy within MySQL. I think MySQL is acquired by Oracle, and the open source community didn't like what Oracle was doing with MySQL. So they did a fork of MySQL, because it used to be an open source database, and that fork became MariaDB. Yeah, so it's in theory compatible with MySQL, and you can just download it independently if you don't want to use MySQL. But just to be clear, that although it's called MySQL within XAMPP, it's actually running MariaDB. But for your purposes, it really doesn't matter. Yeah, it's just basically a version of MySQL. So if you want to install, so the first thing you need to do is get MySQL running on your machines. You need a database management system before you can do anything with a database, right? So one option for you is to just download the MySQL community server. That's what I used to do. Some Macs have a MySQL database running already, but whether it can be a bit fiddly to access it, particularly if you don't know the root password and stuff like that. Yeah, if you do install the MySQL community server from this website, make sure you write down the default password. It sort of appears once when it launches and then it vanishes, never to be seen again. Yeah, so make sure you write it down if you do follow this approach. Yeah. Another way to get MySQL running is with XAMPP, right, which I find a bit easier, right? You just have that XAMPP control panel. You can run it as a portable version. You can run it as a sort of an install. And then all you have to do is click Start, and then it launches the server. Otherwise, with this kind of option, it may well be running in the background, and so maybe impact your performance of the machine a little. Whereas with XAMPP, you can start and stop it really easily, and you don't have to mess around too much, yeah? So you launch up the control panel, or you kind of right-click it in the taskbar if you can't see that. Click on Start, and then you should just see it running like that. Yeah. Now, MySQL on the XAMPP at least ships with a root account that doesn't have a password. Yeah, the community server has a very complicated password you need to write down, but some of the versions of MySQL MariaDB that are shipped come with a root. Just basically the username's root and no password. Yeah, that's great for testing. Yeah. But obviously, if this is a commercial system, you need to fix it and create, fine-tiered accounts, giving as little permissions as possible to the various people. Yeah, I'm not going to cover that here. You can use command line, graphical tools. It's kind of quite a specialized job to understand and do computer security properly. So we're just going to use the standard user account root, no password, for these demonstrations. But just obviously bear that in mind if you ever get into a commercial system. And if you leave MySQL running and don't have a firewall, people can in theory hack into it and do stuff. Yeah. So most database management systems have command line tools associated with them. MySQL has plenty, but sometimes it's easier just using graphical tools. It doesn't really make much difference. So in this course, I'm using Heidi SQL, which runs on Windows. Yeah. So you can just download it. There's a portable version on the course website. Mac OS, just search for MySQL graphical GUI tool or something like that. I'll provide some links in the resources section of the course website. Yeah. So for both Mac and for Windows, the good graphical tools we can use to talk to database. Heidi SQL is one I've chosen to use just because I find it easy and it runs on Windows and you can make it into a portable version. Yeah. So that's Heidi. It's not, not the best in the world, but it certainly does the job quite nicely, and that's what I'm going to be using, yeah? So to get all this running, we start the MySQL relational database management system, using XAMPP in my case. We launch Heidi, connect the two together, and then we can actually start the work of creating and designing databases, yeah? And that's just, sorry, wrong thing there. Basically, this is the kind of connection screen, which I'll show you. And then it comes up and then it's actually connected. Yeah. So let's just do a quick demo of that. Okay. And it's just, I'm not going to bother restarting this thing because it was crashing, as you see. So I'm going to leave it running because it's stable at least. So all you do when it launches, you press start, and then you can see the port appear. And then if I click stop, and if you get problems, maybe you have to reinstall it or fiddle around looking at the error logs. But, you know, this one seemed a little bit unstable. I'm not really sure why, but for the moment it's working, so we'll run with that. And then Heidi, I've got a weird, let me try and find Heidi. Should have done that before. Sorry, the screen resolution is different, so it's, come on. Oh, Heidi, there, please zip it here, yep. So you launch Heidi, which I launch, yeah, and then you get a kind of connection request thing. And then if you're just using the standard root and no password, that probably comes up by default. It's connecting on the local machine, right, and using the standard port, yeah? So open it, and hopefully this hasn't crashed. No, it hasn't crashed. And now we can see the different databases here. So we've got, you know, various ones I've created for various purposes. We can see the various tables and mess around with them if we want to, yeah? Okay, and we'll do a few demos of that in a second, yeah? Let me just still check it's still running because yeah, some issues with that. Okay, so let's get back up with this. I think it's running it. Yep. Okay, so I have got portable versions of the software, though they're slightly out of date, but they should all work and run. So if you're working in the labs, obviously if you install XAMPP or install MySQL on a lab machine, then the next time you go back, all your database will have gone. So it's sort of easier using a portable version on a USB stick for running the database on the lab machines, if that's what you're doing, instead of running it on your laptop. If you're running on a laptop, you can just install these things on your laptop, yeah? Okay. So let's go into how relational databases work. And obviously, if you know all this stuff, you can just sort of skip forward in the video. This is meant to be a sort of very basic kind of introduction just to get you going with this, yeah? So how they're organized is you have one or more databases, and these might hold data for a particular project or website, yeah? So you might have a database for, you know, your e-commerce website, a database for your game website, and so on and so forth, yeah? Within a database, the data is grouped into tables. So you might have like employees, jobs, blogs, etc. These are holding data of a similar type, yeah? Within the table, you have columns. These are a sort of fine breakdown of the different pieces of data in the tables. So, for example, an employee might have an ID, a name, an address, and so on and so forth. And because relational databases are trying to constrain the data as much as possible, then the data within each column has to be a specific type. So your email address might have to be a text, your phone number would be an integer, a price of a product might be a float, and so on and so forth, yeah? And then the data within each table is organized into rows. So here's a sort of classic example. We got like 3 different tables here. We got a cereals table, a cereal boxes table, and a comparison table. And then each of these here in the database design, these are the sort of headers on the column, right? We've got an ID, name, description, image, URL for each of the cereals. And you can see here we're using types here to specify, and there's quite a lot of complicated types. You know, back in the day, everyone cared desperately about storage. These days, we don't worry so much. So people, you know, would even specify the number of characters to store for each of these things. But these days, people don't really worry so much about that. And price, actually wrong here, that should be a float, right? So, or, yeah, float. So try and get these right, because otherwise you won't be able to store the appropriate data in those columns, yeah? And then if we actually look at the table here, some rows in the table, right? So we've got the ID, you know, the name, description, and this is all kind of gone through in a bit more detail in the lecture on SQL, yeah? So you can just sit there happily at the command line using an SQL command line tool to send SQL commands to the database management system in order to create the databases and tables, yeah? Or even within Heidi, we can actually type in SQL commands and run them on the database management system. So we could do all this creation of tables and databases and so on and so forth using SQL commands, and when you back up your database, you'll see that it's actually creating what it's outputting are the SQL commands used to create the structure of the database, yeah? But again, there's not a lot of point in learning that, particularly for this course. So we're going to use a graphical tool to create our database and create our tables in that database, yeah? And I'll show you how to do this using Heidi SQL. Right, so going back to Heidi, and just check it, like I said, there's some crashing issues, but that's fine, right? Okay, so let's create a new database. It's very easy, right? We just right-click here and do create new database. and we'll call this, I don't know, demo 1 or something. Okay, and with a bit of luck that will work. Okay, so that's our database, and then we want to create a table. We will create a new table, and we'll call this table, let's call it customers, and then, so we give the table a name here, and then we can add columns to this table. So I'll come to this later, but we'll give this a primary key, create new primary. I'll maybe do another one later for that, but just call this name. And you see here we can select the data type. So ID name is fine. I know I'm about to cover that, but this is just a little demo about creating the thing. And then we can add kind of address, for example, and that's text. Yeah. So we basically configure our table. I'll do another example later explaining what this primary key stuff means. But we add all our fields here, all our columns, and then we just click on save, and then it's created our customers, and we can see all the data there. Yeah. Okay, so having just sort of whipped through that, I'll now go properly into what I mean by primary keys and foreign keys. Yeah. So in relational databases, each row in each table has a primary key associated with it. Yeah. So every row has to have a unique primary key. And there's different options for what you want to use your primary key. I mean, one classic thing would be to use a unique field as a primary key. For example, if you know that each of your customers has a unique email address, then you can just use the email address as the primary key, or in the case of students, maybe the student number. You can also use combinations of fields. So, for example, if you knew that the first name, last name, and birthday is going to be unique in your table, I mean, obviously you might get the odd exceptions to that, but in general, you could probably assume that. So in that case, we could use that combination of fields as our primary key. You can create your own primary key, typically an integer. And I could, if I wanted, whenever I put a new piece of data in the table, create my own unique integer and use that as the primary key. Yeah. The problem with that is you can only have one. Each primary key has to be unique, so I'd have to have some mechanism keeping track of primary keys and making sure I didn't put one that was already existed in the database. Yeah. So the easiest way to handle primary keys with relational databases is to just configure the relational database management system to automatically create new primary keys when data is added to the table. Then you can just insert the data, and it will automatically add a unique primary key for you, usually just in increasing numbers. Yeah. So here's our tables here. So we have a customer, so in the order, and both of these have a primary key that will be unique for each row in that table, in those tables. Yeah. So with Heidi SQL, all you have to do is right-click on the column that you want to make into a primary key, and then you choose Create New Index Primary. And if you want this automatic feature, where it kind of automatically creates a new primary key whenever you insert data, then you just select the Auto Increment field. So I've already done this once, but I wasn't going to explain what I was doing, so I'll do it again. Yeah. So let's create our orders field. Yeah. Let's add a new table. We'll call that orders, right? So let's just do. So here's my primary key field here. So data type integer. That's sensible. And then we can default to auto increment. That means it'll automatically add our new primary key for us. And then we right click on this and do create new index primary, and there we have our primary key, and you can see that key thing showing up there in the sort of orangey yellow kind of color. Yeah, these are orders. So I'm not going to finish this one actually, because let's just call product, for example. I don't know, it doesn't really matter what we put. I'm not going to finish this because I want to show foreign keys as well, but then we basically put all our fields in here and we click on save, and then that's our table with our primary key. Now, the other kind of key you need to be aware of within relational databases are foreign keys, yeah? And that's a field in one table that refers to a primary key in another table. And so this is saying there's a dependency relationship between two tables. So obviously we're trying to build up this data structure in a very consistent and logical way. And so these foreign keys are basically saying that this row in this table can point to a row in another table and have a relationship between them, yeah? And then obviously to maintain consistency, if we're updating or deleting data in one row, we might need to change the other row as well, or check that other row exists. So if I delete a row that's being pointed to by another row, then I need to make a decision on how we kind of handle that. Yeah. So we could, if I delete, for example, a customer from my database, I might want to delete all the orders associated with that customer. That's a cascade operation. Or I might just want to block actions because I want to make sure, I might want to keep those orders, but not allow you to just randomly delete customers without making sure that we actually want to delete the orders as well. Yeah. So this is a classic foreign key. Here we have the order, and here we've got a customer ID here pointing to the primary key of the customer table. Yeah. And we've got products, order date, price. Yeah. So in Heidi, it's very easy. It has this foreign keys tab, and so we can just use that to add foreign keys. And I'll just sort of show you here. Yeah. So here I've got a product. Let's just get rid of that. Let's just say I don't know, shipping address. And let's just do price. I'm not going to put products because that's a bit of a tricky one because as I come to database design later, but we'll just do price will be a float. Yeah. Oh yeah, and then we want customer ID. That's the whole point of this, right? So putting the customer ID here. So the type has to be right. Obviously, it can be an integer. So now we've got all this lot, yeah, and then we can use the foreign keys tab to say that. No, maybe I need to say that first. Okay, then we need to add a foreign key. Now we want to say which of these columns is the foreign key. In this case, it's the customer ID. And that's referencing the table customers. And the column in customers that I want to reference is the ID column, yeah? So we're saying which column in this table is we want to be the foreign key, which table that column's pointing to, and then the actual column in that reference table, yeah? And then we can choose the restrict, which basically, I think it blocks the operation to maintain consistency if that's appropriate, yeah? So we save that, and we can see here we get this green key appearing here, indicating this is a foreign key. Okay, so in this section, so that's the sort of basics, right? We have tables, tables have primary keys, and then we have relationships or foreign key relationships between these different tables. That's the basics of relational databases, yeah? So now I'm going to explain how we can design these databases and some of the rules that have been developed in order to design good, consistent databases, yeah? Now, databases can be really big, right? Kind of millions of rows of data, and we're paying to store our data. And we also want to make sure, so we don't want to have like lots of redundant data in our databases, not only because it costs money, but because redundant data can make it harder to update our data and maintain our databases, yeah? So we want to design our database in an efficient, logical way that minimizes storage space, minimizes access time, and makes it easy to maintain consistency. If I have the same data in multiple different places, then changing the data, say I've got your customer address stored in orders and customer address stored somewhere else, then to change the customer address, I've got to change it in 3 places, whereas if I have a good database design, I only have to change the customer address in 1 place, yeah? So over time, people develop these rules that people can use to help maintain this, to help them design good databases. And this is a process called data normalization. And what you have is what's called these different normal forms. So the first normal form, there's about 5 or 6 of these, plus Boyce code normal form. In this lecture, I'm only going to worry about the first 3, just to give you an introduction to these ideas, yeah? So the first normal form rule is that each column should contain a single value, and there's a single type of values in each column, yeah? And each column has a unique name, and the order in which the data is stored doesn't matter. So, I mean, these are easier shown through examples, yeah? So you might think we could design a database like this, right? We have the ID, the first name, last name, and the courses that they're studying, yeah? And we're just using kind of a comma to kind of separate these different courses, yeah? I mean, that's kind of a rubbish design anyway, because we obviously want to point to a separate courses table, probably. But it breaks first normal form because you're using this kind of comma-separated list instead of having a unique value in each field, yeah? So that's what's broken it, yeah? So in this case, we have to do, I mean, this is still rubbish design, and we've got, for some reason, duplicate IDs, which doesn't make sense, but let's ignore that for the moment. But to make it first normal form, at least, we've taken those multiple values within the fields and turned them into single values. And then at least we're passing first normal form. As I said, there's some other big problems with the table, but we'll set those aside for the moment, yeah? So second normal form, it has to be in first normal form. And what we can't have in second normal form are partial dependencies, yeah? So as I mentioned earlier, the primary key can just be a unique value, single single value like ID or email address, something like that. But sometimes people use multiple values for the primary key, multiple columns for the final primary key. Yeah? And a partial dependency occurs when one part of the data depends on one part of the primary key, and another part of the data depends on another part of the primary key. Again, much easier to see with examples. So here we've got our table here. We've got student ID, project ID, student name, and project name. So this is a partial dependency. So sorry, here, and this is a primary key here is a combination of student ID and project ID. Yeah, it's both of these together make up the unique thing that defines each row. Yeah. So we've got two partial dependencies in the table. Obviously, student name depends on student ID, which is one half of the primary key. And then we have project name depends on project ID, which is the other part of the primary key. Yeah? So we've got these two sort of partial dependencies here within the table, and that's why it's breaking second normal form. So to fix that, we did the obvious thing, right? Most of these things are really obvious, yeah? And we just sort of split them out. So we have one table storing student ID, student name, and the project ID, for example. And then the project ID here is stored, the projects are stored in a separate table. And here we've got the primary key here is the student ID, the primary key here is the project ID. We've only got, the primary key is only a single column, so now we don't have to worry about partial dependencies, and therefore we're in second normal form. Still a terrible design, but at least it, it gets us towards a better design, yeah? Now, third normal form, the rule is obviously it has to be in second normal form and that you don't have what's called transitive dependencies. And transitive dependency occurs when you've got data in one column depending on data in another column that's not the primary key. So this isn't about primary keys anymore. This is about dependencies within the data that's stored within the table. Yeah. So suppose we've got this table here. Now this is in second normal form because the primary key here is just the ID. But we still have, it's not in third normal form because there's a transitive dependency here, yeah? Because obviously the campus address depends on the campus, like obviously. It doesn't depend on the primary key here, yeah? So that's what's called a transitive dependency because the one column within the table depends on another column, not on the primary key, and that's why it's not in third normal form. And I'll give you another example of this when we're talking about designing your e-commerce website databases, yeah? So it's obviously a thing we can do to make it much more efficient as well, right? Because you can see these rules are actually helping with this efficiency here, yeah? Because here we're storing campus and campus address. We store the campus address 3 times, which is really no need to. Whereas here, by turning this into third normal form, we're only storing the campus address in one place, and that's going to make it much easier if the campus moves to a different location, yeah? So here we've got the student data here, and then there's a foreign key relationship between the student data and which campus that student is in, yeah? So again, so now we're in third normal form, and you can also see, I hope, that this has produced a much nicer database design. There's quite a lot of theoretical and technical work on different forms of normalization. So there's Boyce-Codd normal form, fourth normal form, fifth normal form. I'm not going to go into all this, and just if you get your head clearly around the first 3, then that's a great start, and that's what I'm hoping for with coursework 1. Yeah. I am expecting your databases to be in third normal form. I'm not, but if you want to, of course, by all means look into it and get into the other forms of normalization. But the expectation is just third normal form, and that's fine. That should produce a reasonably good design, I think. Yeah, and there's like a couple of marks for that in coursework 1. Now, another tip I'm going to give you for database design in coursework 1 is a mistake that a lot of students make because they sort of think it's like better, but it's really not. One thing you should do is avoid using tables that hold a single value, possibly with an ID kind of thing. And I'll explain what I mean. But what this does, if you do this, you're just basically adding complexity, making it much harder to get the data you need out of the database. So just don't do this, basically. And this is kind of what I mean here. Yeah. Suppose we had our students, and then the students, you might think it's a good idea to have a sort of this kind of relationship here where we have a student, instead of putting the email in the student table, we'd put the email in a separate table and then have a foreign key relationship here just to point to that email. Now, in some cases, if the student had multiple emails, maybe that would make sense. We might have to have a separate table holding the student ID and the email address, maybe. But in this case, it makes no sense whatsoever, right? Because it's just pointing to this field here. And what we could easily do to make our lives simpler is paste this email into the student table and merge these 2 tables, yeah? So don't ever have a separate table for the sake of it, that just to hold a single value, yeah? It doesn't make any sense at all, yeah? As a general rule, your databases need to be in third normal form, but don't expand them thinking that's going to help you and put lots of extra stuff in them. You know, the more tables you've got, the harder work it's going to be to make for the web scraping and the storage of data, and for the web service and retrieval of data. Yeah, those are going to be much harder with more tables. So just minimize it, but don't minimize it so far that it breaks third normal form. So yeah, we can just replace this with this simpler design. You know, it makes a lot more sense. Yeah. Now, it's quite difficult to design databases, yeah, and there's no hard and fast rules, really. We've got the hard and fast rules, sorry, but there's also a bit of art and a bit of thinking, and it'll vary with the kind of data. Obviously, with some kind of very well-established things like e-commerce websites, there'll be some fairly standard designs that you can sort of lean on. But with something new, you're going to have to sit down and think about it carefully about how on earth to do it. Yeah, you maybe got to do several drafts. Now, to do your database design for the proposal, you can do pen and paper, you can use Word. I use DB Designer, and I'll use that in the lectures and demos and stuff, because that's quite a nice sort of interface for designing different databases, and you can just quickly see what they look like. Yeah, many other tools are available, but always be prepared to modify your design as you develop a better understanding of data. So yeah, so if you come in the proposal, if you come up with a design, maybe I'll give some feedback about it, about how it could be improved, then go away and you have a think about it and maybe make changes for your final database. Yeah. Now, to help you along with this process, I'll talk you through some of the issues to do with database design that are going to come up with your comparison website. Yeah. So here, my example of cereals, right? So we know what cereals are, like breakfast cereals, what I'm talking about, not, you know, cereal crops, right? So we're talking, you know, Kellogg's Cornflakes, Frosties, you know, Weetabix, all that kind of stuff. Yeah. So the first thing we need to think about is what kind of thing are we dealing here? We want a price comparison website, and we want to do that for cereals. Yeah. So obviously we have different types of cereal, cornflakes, fruit and fiber, etc. Different people make these different types of cereal, right? We might have Kellogg's Cornflakes, Tesco Cornflakes, Asda Cornflakes, and so forth. And not only different people make these things, but different people sell these things, yeah? So I might be able to buy, so I can buy Kellogg's Cornflakes from Tesco, Waitrose, etc. And there's another problem with cereals, that they come in different size boxes, right? And maybe I've got a 500 gram box of Kellogg's Cornflakes. I might also have a 1,000 gram box of Kellogg's Cornflakes, which will have different prices associated with them, yeah? So let's just start off with a simple bad design, and then I'll show you why this is a problem, and we can talk about better versions of this, yeah? So you might think we could just shove everything together in a single table. So we've got like a single table called cereals. It's got an ID, name, description, image URL, maybe the size, the price, and URL, yeah? And so here we got, you know, an example of this table, right? So everything's in here. And then we got, so remember this price comparison website, yeah? So I want to be able to store the URL where I can buy 500 gram box of Kellogg's Cornflakes at $2.99, yeah? Or the URL where I can buy 1,000 gram box of Kellogg's Cornflakes at $3.99. Yeah, we're storing the relationship between places where I can buy things and the price that I can buy them and what those things are, yeah? Now, from a point of view of, you know, normal form, third normal form, we can see we've got some transitive dependencies. Just like the example with Hendon and campuses, right? The description of Kellogg's Cornflakes depends on the name here, Kellogg's Cornflakes. It doesn't depend on the ID of the field. So we've broken third normal form with this design, yeah? And you can see here that obviously we're storing the description here of Kellogg's Cornflakes 3 times, yeah? So it's a very inefficient design, because if we want to change the description of Kellogg's Cornflakes, we're going to have to change it in lots and lots of places, yeah? Because they're potentially going to have millions of entries here, yeah? Or thousands, hundreds of thousands of entries, yeah? So this breaks the third normal form already. And it also breaks third normal form here, right? Because the price is linked to the URL where you can buy the cornflakes. The price here doesn't depend on the primary key, yeah? So that seems, you know, suspicious at the very best, yeah? So an obvious first step is to split this out to get rid of this transitive dependency on the right here, yeah? We might have a separate table for comparison that stores the relationship between the URL, the price, and the serial ID. This is quite nice. We've got rid of the second transitive dependency. And then we might have a separate table for the cereals, where we've got the ID, name, description, image, URL, and size, yeah? This doesn't eliminate, the problem here is we haven't fully eliminated the transit. So here's our second design, right? We've got our cereals table, and we've got our comparison table. You can see here we still haven't completely eliminated the transitive dependency, because here we've got the description still depends on Kellogg's Cornflakes, because we have different sizes of Kellogg's cornflakes. Yeah. So by mixing up the size with the name, description, the image URL, we're introducing duplicate data in our database, which is going to cause maintenance problems. It's going to cost us more money to store, and it breaks third normal form, so you're going to lose some marks for it. Yeah. So here we can go for the final design. I mean, this is my final design. Maybe you can come up with a better one, where we have a cereals here. So these are the different. So the cereals here would be like Kellogg's cornflakes, Asda cornflakes, Kellogg's fruit and fiber, Asda fruit and fiber, Tesco fruit and fiber. All the different types of cereal. That means that basically the product that goes inside the box. And then here we have a cereal boxes table to hold the different sizes of box that these cereals are available in. Yeah. So we might have 500 grams of Tesco's fruit and fiber, 1,000 grams of Tesco's fruit and fiber, and so on and so forth. Yeah. And the cereal boxes, this table in the middle, is what's actually sold to the customer. You can't buy a cereal in the abstract. You can buy a box of cereal, and that box of cereal will have a different price on different websites. And so the comparison table here stores the URL where that box of cereal is available and the price at which it's available. Yeah. So it's splitting out the sort of abstract description of the product, the box you can actually buy, and the comparison and the price and the URL where you can buy it. Yeah. And so this is an example. You can see here we've got rid of the duplicate descriptions of the Kellogg's cornflakes, and we've got then we're linking the different products with the different boxes which you can buy, and then we got the comparison table here where you can actually see the prices of those different boxes. Yeah. Now I've teaching this course over for, I don't know, 5 years, something like that, and I found that most comparison designs fit into this model. So you have one table to hold the data about the products. This isn't something you can buy. This is a description of the different types of things you can buy. Yeah, it's not an actual product. Yeah, it's just data about the products. Yeah, and then the second table holds data about product variations. Yeah, so this might be the size of a box of cereal, something like that. And then the third table will hold the comparison data. So if we were buying books, for example, you have the actual kind of text of the book, yeah, written by a particular author. But you can't actually buy that text sort of in the abstract. You have to buy particular versions of that text. You can buy an ebook, you can buy a Kindle version, well, it's kind of the same. You buy hardback, a paperback, and so on and so forth, yeah? So with books, you'd have one table for describing the book text, so to speak, and the author and all that kind of stuff, cover image, that kind of thing. You'd have a middle table would be the book variations, like ebook, hardbacks, paperback. That second middle table could use the ISBN numbers, and then the final table would be the comparison showing the prices for that particular book on different websites. Yeah. And if we're doing shoes, same thing, right? We have shoe models like Nike Air or whatever, and then we have sizes of shoes which go into the middle table, and then the final table would have the comparison, how much it would cost to buy a size 12 Nike Air on Tesco's, for example. Yeah. And this is true of bicycles, whichever thing it goes on mobile phones. It's the same basic idea. With mobile phones, you'd have the kind of Apple iPhone 11 type thing with a picture and a product description. The middle table will hold the variations on that, how much memory, all this kind of stuff, right? Maybe screen size, color. And then the third table will then hold the price at which that particular iPhone you can buy would have the price of that on different websites. Yeah? Okay. So we designed our database, we built our database. Final thing I want to talk about is backing up database. Yeah. So almost inevitably, your website will get hacked, right? If you're building a commercial website, people try and hack them all the time, and often they succeed. Yeah. If you just got a local website, pre-coursework or something, guarantee it, the hard drive will fail at some point. Hard drives do not last forever. Yeah. Or it'll be stolen, or you'll lose your laptop or something like that. Yeah. Or if you're running your own kind of servers, then the server room will flood. Even Amazon goes down from time to time. Yeah. So you should always regularly back up your databases. If you're running a business, your customers' data is your business, yeah? If you lose the data of all your customers, you are really stuffed, yeah? Particularly if you've got a lot of customers, yeah? So you should always regularly back up your database and always back up the structure of the database and data in the database. And obviously you need to store this backup securely somewhere in accordance with various laws to do with personal data if you're a real company, yeah? So here's a couple of tools you can use to do this, yeah? So MySQL dump, backing up an MySQL database, then MySQL dump is a very good tool for this, yeah? If you're running a commercial system, you could just run this in the background every day and automatically put that dump in a secure location and secure different physical location, yeah? In XAMPP, if you're running XAMPP on Windows, you can just find MySQL dump in XAMPP MySQL bin. Probably the same true as using MAMP or XAMPP on a Mac, although you obviously have to dig around a bit to find the actual bin folder, yeah? obviously this isn't this. So what MySQL dump? It's a command line tool that talks to the database management system and pulls the entire database in SQL format and saves it into a file. Yeah. So obviously the database management system needs to be running, otherwise MySQL dump's not going to work. Yeah. So it's just command line tool. So this is the kind of syntax. You specify the program, MySQL dump, the user and the password, the database you want to back up, and then this is the file where you want the SQL to be stored. Yeah. So I'll just sort of demo this, probably easier. Yeah. So let me see if I can find this thing. Okay, so here just to show you it. Yeah, see XAMPP, MySQL. Bin, right? So there, it's in there somewhere. Yeah, I just dug it up the other day, just now. My SQL dump. There you go. So there it is. Yeah. So if we're doing this, we need to run it. We can't just run it from there because we need to provide the parameters. So we go into PowerShell if you're on Windows, or you know, the shell on Mac. Yeah. And then to back it up, we just, in this case, be MySQL dump. Have the user, then the root. User root. I don't need a password because I don't have a password. This is the database I'm backing up. I'm going to pipe it to C temp dump. Yeah, I mean if I just piped it, in fact I'll just pipe it to the local one to show you. Yeah. So if I do dump, I think I've got dump already, but if I do dump to SQL, right? So run that. It runs very quickly because it's a tiny database. Yeah. And then if you look in here, you see you got dump to. Double click on it, and so here where I've dumped both the structure of the database. Okay, so here is, you can see it's creating table, dropping table if it exists, so on and so forth, and it's also dumped the wait a minute, does this have any data in it? Actually, that's a bit weird. Let me just check. This is which am I dumping? SQL lecture 2. Maybe I don't have any data in these things yet. Oh, I do have data. Why hasn't that worked? Okay, not entirely sure that hasn't dumped data, but should have dumped data. Yeah, dump to, let's dump the data. What you should see anyway. Oh yeah, wait a minute, it has done it, I think. Yeah, it has done the data. Sorry, just missing it because it's such a tiny amount of data. Yeah, so it's dumped the structure of the data, the structure of the tables there. Okay, and then here it's also dumped the data. Yeah, so obviously with your comparison one, you actually see enormous amounts of data. I just missed that because I wasn't looking very carefully. But this is actually, you've got these insert statements here, which means it's actually dumped the data as well. So it's inserting into the tables the data that I've stored there. Yeah. So this is a backup. Now the crucial thing about this backup is it's in text format. Okay, I can read it. This is just standard Notepad++ text editor. You will not get any marks for dumping in some kind of weird binary format or copying the binary files or anything like that. Yeah, it must be readable. It must be an SQL file that I can look at in a text editor like this. Yeah. And then what you do after, if I wanted to restore my database, I could then basically send all those commands back to the relational database management system, and it would reconstruct that database for me. Yeah, so this is how it kind of backs things up. Yeah. The other way we can do this is with Heidi SQL. Yeah, and you know, it's probably easier if I just show you. Let's just do it. Okay. Wait a minute, no, I've lost. Where's Heidi gone? Okay, it's Heidi. So suppose I want to back up this kind of serials thing here. I can go to Tools, Export Data as SQL. Now, make sure you choose Inserts or Replace Existing Data. Choose one of the data options, yeah? And make sure you're choosing the Database and Tables Create options, yeah? Single SQL file, and then we can just do, I'll dump it into temp, right? Dump, call it dump demo. And why is that not giving me an option here? Oh, I'm selecting. No, right, yes. Several things you need to do, yeah. Select data. But you obviously need to select the database you actually want to dump as well, yeah. So I'm selecting here SQL Lecture 2 because it's the one I was playing around with earlier. And choose Create here, the tables. Data replace existing data. So I've selected my database, selected where it wants to go, then I click on Export. Now, where did I put it? I think I put it in temp. No, I put it in C temp, I think. C temp. And dump demo. So again, when you do a dump, don't assume it's right. It may not be. Yeah, and obviously I can help you with this in the labs. What you must do is open it up and make sure it's right. So I can see here it's creating database, it's creating the tables, and here it's putting in the data that I've stored in the database. Yeah. So this dump has both the table structure as well as the data, and if it didn't have the data, it doesn't really matter either way. But you can always dump both automatically all the time, which is probably what you want to do. But for your proposals, you're just going to want to dump the structure anyway, so it doesn't really matter about the data, and you won't have any data anyway. Yeah. So this is what I'm expecting to see for your proposals. It should be creating these different tables and maybe creating the database as well. Yeah. Now, when you're doing your dump, be very careful that the capitalization and the structure of your databases matches that of your diagram that I'm asking you to do. Yeah, if it doesn't match it, you're going to lose marks. Yeah, because I'm asking your documentation should always match what you've created. Yeah, so your SQL dump must match the documentation in your project report and your proposals. Yeah. Okay. Why can't I see my mouse? It's wrong way. Okay. Ugh, come on. So I'm just getting there. Alright, let's just... Okay, yep, so I've shown you how to back up with Hardy SQL, and I've shown you the output you get, yeah. Okay, so for the proposal, I'm only expecting the commands used to create the database. If you put some data in there, it doesn't really matter, but you must have the commands and it must be readable in a text editor. And for the final project report, I'm expecting an SQL file, SQL dump of the entire database with the data inside it, yeah? Again, you'll lose marks if you don't dump the data, and it'll be harder for me to mark your projects unless you include the data as well, which will give me some idea of how successful your project has been, yeah? So always, you must be able to open an SQL dump in a text editor. It must contain SQL, obviously, yeah? If it's not readable in a text editor, no marks, yeah? Your database diagram must match the SQL commands, yeah? If your tables in your diagrams look completely different from your SQL, you're going to lose marks, yeah? Obviously, make sure the commands create database and tables have been correctly dumped for your proposal. And please, please, please check that the data's in there and ask me for help if you can't dump the data correctly as well as the table structure, yeah? And the names must match, capitalization, spelling, all of it, because I'll knock off marks without hesitation if you don't do that, yeah? Okay, I think I've covered that, yeah? Okay, so this lecture introduced relational databases, shown you how to get a relational database management system and associated graphical interface running, covered the principles of database design of a third normal form, and explained about database dumping, yeah? That's it.